Absorption coefficient is alpha, which is given here. We have the scattering coefficient sigma s, which is given here. Sigma is the Stephen-Boltzmann's constant, which is also included in this equation. I is the radiation intensity, which depends on position and direction. T is the local temperature, which is used here. Phi is the phase function, which is this phi, and ohm is the solid angle, which is shown here. So this is the radiative heat transfer equation, which is solved in order to capture radiation phenomenon. This is basically a transport equation for radiation intensity. It considers the transport of radiation intensity, the reduction in radiation intensity because of scattering and absorption, and it considers the linking of with energy equation and temperature coming from the boundary as well. Intensity along any direction can be augmented by local emission and in scattering, that is scattering into the direction. This changes the radiation quantity. So fundamentally, based on this equation, there are 4 common radiation models which are used. There is the discrete ordinate model, discrete transfer radiation model, the P1 model, and the S2S model. So we will see one by one all these 4 models and how to set them up in the Fluent software. Let us see what are the steps involved in setting up the radiation model in Fluent software. This is applicable to general thermal analysis in which we require radiation model. So these are the common steps to set up any radiation problem. First, we will see all the workflow steps, and then we will go into detail of each radiation model. The first step is to activate the energy equation. Then we activate the radiation by selecting any one of the radiation model. So we activate the energy equation here. That is done here. Then we go to the radiation panel, which is done by clicking on radiation, which is given here, and we use any of the radiation models that are shown here. In the second step, we set the appropriate radiation parameters. Each radiation model requires some input parameters. As shown in the P1 model, we require wavelength interval and number of bands. So this is an example of the dialog box for the P1 radiation model. So what we have done here is we have selected the P1 radiation model, and these are the various inputs needed for that model. So we also have to fill up these inputs. In the third step, we input the material property related to radiation. Property like absorption coefficient, scattering coefficient, refractive index, scattering phase function are required for materials to be assigned in the CFD model. These properties are required to make internal radiation equation calculations. These properties, if they vary with temperature, then those inputs are also required to be given. Also, we have to define properties for solid as well as fluids to be used in the CFD model. So for defining material properties related to radiation, we go to materials, click on the material, then click on edit. After we open the dialog box for editing material, there are various radiation properties like absorption coefficient, scattering coefficient, scattering phase function, refractive index, which we input as material properties for radiation. In next step, we define solver parameters. These include under relaxation parameters. After we define material properties, we have to assign the boundary conditions. Some thermal boundary conditions are required to for solving radiation. The important is for wall boundary condition is the emissivity boundary condition value. We have to define this for all boundaries in the CFD model. So in case we have wall boundary condition, when we go and click on boundary condition, we select the wall, click on edit. After that, we go to that particular wall boundary condition edit dialog box. Here we have to set emissivity for that particular wall. This is important boundary condition. Next are the solver parameters. These include under relaxation factors for radiation equations similar to the momentum and energy equation. This is only required for DTRM, DO, S2S and P1 model. For setting the under relaxation factor, we go to solutions, solver control, and then we set for that particular radiation model similar to the energy equation, we set a under relaxation parameter or under relaxation factor. After that, we initialize the model with initial values. These are extremely important for transient simulations. Then we press run and start the simulation. So for starting calculations, we press here on calculate. Before calculating, we also have to initialize the solution as shown here. Then we press run and start the simulation after obtaining convergence. There are also post-processing options specific to radiation, but we will see them later in this particular course. We will follow the following learning pattern for all radiation models. First, we will try to quickly see what is the concept of the radiation model. This will give us a glimpse of what happens behind the software. The equation used for each radiation models will be highlighted. Then we will see the advantages and limitations of each model. After that, we will learn the steps required to set up the radiation model in Fluent. So the first is the P1 model. This model solves the simple diffusion equations taking radiation intensity as the variable. This is like replacing temperature from diffusion equation by incident radiation as the variable to be solved. The value used for incident radiation is the sum of all radiation intensity in all directions. As shown in this equation, we have the diffusion term, the emission term, and the absorption term. In short, the balance says that the net amount of radiation, which is the balance of emission and absorption, is the diffused quantity. But there is also scattering of radiation which is not present in the equation. So how does that effect come into picture? For that, diffusivity is altered as shown in this equation. This is basically the diffusivity, which is now a function of a lot of parameters. Let us see what those are in detail. This empirical relation of diffusivity is taking care of scattering. In this equation, the parameter C is known as linear anisotropic phase function coefficient. It can take values from -1 to 1. C is negative if the fraction of radiant is scattered in backward direction of the incident direction, and positive if the radiation energy of rays are scattered in the same direction as the incident radiation. After this, the radiation flux is calculated from incident radiation quantity G by using its space gradient and diffusivity. What are the advantages of the P1 model? This is a very simple model as it solves a single diffusion equation. It does not require much computation power, so a small memory machine is sufficient. Our calculations are quicker. It takes into effect the scattering of radiation as well, but it comes with limitations also or disadvantages. The participation media must be optically thick, which means absorption should be high. This model also tends to overpredict radiative heat flux at localized area having heat source or sink, so it loses accuracy in such area or in such models. It does not consider specular reflection. As you can see, the P1 model is very quick and easy to use, but if you are looking to consider each and every detail of radiation phenomenon, this is not the most preferred model. Now let us learn how to actually use the P1 model or set up the P1 model in the Fluent software. First, we need to activate the P1 model. Now the original equation of P1 model which we saw was meant for gray radiation only. Nowhere in the equation we saw that there was any quantity which was function of wavelength. So by default, P1 model will solve gray radiation only. If we want to solve non-gray radiation, which means real conditions in which radiation properties and quantities are varying with wavelength, we have to give additional inputs. First, we have to input the number of bands, which means the wavelength slots for which we need to consider non-gray radiation. So this is basically the number of bands for which we have to consider non-gray radiation. Then we need to define each wavelength band. We can also name them and define the start and end wavelength of each band. So the name of each band is given here. As you can see, the name of the band and the start wavelength and end wavelength is given here. This is the second band, start wavelength and the end wavelength. The P1 model will consider the non-gray radiation effects in those wavelength bands. That was about the P1 radiation model. Now let us move to next radiation model, which is the DTRM. DTRM stands for Discrete Transfer Radiation Model. The main assumption of the DTRM is that radiation leaving the surface element in a certain range of solid angles can be approximated by a single ray. So now the radiation transfer equation is solved along a single line or straight line. The DTRM integrates this intensity equation and comes up with this equation now. The integration is done along a series of rays starting from boundary faces. The azimuthal and polar direction coordinates are used to define the rays used in DTRM. When the solver integrates the radiative transport equation, we get what is seen in the second equation shown. The DTRM determines the new intensity IS using the radiant intensity at the start of the incremental path, which comes from the boundary condition, that is I0 or I0. So this is the new intensity. This is the intensity which comes from boundary condition. The energy source in the fluid due to radiation is then computed by summing the change in the intensity along path of each ray that is traced to the fluid control volume. This ray tracing technique used in DTRM can provide a prediction of radiative heat transfer between surfaces without the need to calculate view factor. Thus, the lesser the rays that are traced, lesser the accuracy, and also if mesh is coarse, the accuracy reduces. Now let us see the advantages and limitations of the DTRM radiation. The biggest advantage or importance of the DTRM is that it has a direction sense. It considers radiation rays in terms of tracing, but this model also has limitations. This model cannot account for scattering like the P1 model. The model does not consider particle and radiation interaction. As it considers rays, it is computationally expensive than the P1 model. Gray gas approximation is there, which means no wavelength effect. It is not valid for parallel solver, can give issues with heat balance, and the best result is only with optical thin medium. Now let us learn how to set up this model. After we activate the energy equation, the radiation options come. There we have to select DTRM and click OK. After this, DTRM rays dialog box will open as shown here. Now it is here that we input parameters for creating rays and clusters. We input the number of surfaces that are participating in radiating rays. We select the absorbing cells also. We set the cells per volume cluster and faces per surface cluster. We also set the number of theta divisions and phi divisions for angular discretization. This will decide angular discretization and formation of ray, which is the basic assumption of DTRM. That is, radiation from certain solid angle region can be approximated by a single ray. Then click OK in the DTRM dialog box. After that, the select dialog box will open. Enter the name of the ray file and decide whether to write a binary file. Now ANSYS Fluent will make the ray calculations, write the ray file and read it afterward. During the writing process, the status of the DTRM ray tracing will be reported in ANSYS Fluent console as shown here. So this is the status of ray file writing. Now we have seen in the earlier slides that DTRM works on the principle that we convert the total region of radiation into smaller solid angle sectors, and a ray is emitted from each such sector. Now we can further make groups of cell volumes and surface areas as well in order to reduce the computation effort required. Hence, we need more inputs for DTRM. First is the cell per volume cluster and second is the face per surface cluster. The cells per unit volume will decide the number of radiating surfaces and absorbing cells. The default value is 1. This means the number of surface clusters, that is radiating surface, is equal to the number of boundary faces. The number of volume clusters, that is absorbing cells, will be the number of cells in the domain. For large and complex problem and geometries, we must reduce the number of surface and volume clusters in order to reduce the ray tracing expense or computational requirement. We have to decide how many surfaces participate in radiation by setting the number of surface cluster. But we still can input or control the number of rays which are being traced from each surface cluster. For that, control parameters are theta and phi divisions. The theta division is the number of discrete divisions in the angle used to define the solid angle about a point on a surface. The default setting is 1, which means there is one ray traced from the surface. The phi divisions are the number of discrete divisions in the angle used to define solid angle about a point on the surface. The value varies from 0 to 360. The default value is 4. This means each ray that is traced from the surface will be located at 90-degree angle. Default setting of 1 for theta and 4 for phi combined means that 4 rays will be traced from each surface control volume. We should at least double the default in order to get meaningful result.